All right, so today we'll carry on with chapter three. Last time, if you remember, we finished up section 3.1. So we'll go now to 3.2 and carry on from there. So we're going to look at a couple of interesting theorems in this section. And one of them is called Raleigh's theorem, as you can see there. And what is this theorem telling us? Well, let's look at the formal definition. It's saying here that if f is a continuous function on the closed interval ab, and in addition, differentiable on the open interval a to b, which basically means that it could potentially have sharp breaks at the two endpoints, which would mean there's no derivative there. They're guaranteed as long as f of a equals f of b, there's at least one number in this interval where f prime of c equals zero, which is the same thing as saying that the tangent line is horizontal. Okay, so they have a nice graph of that here. Let's take a look. I'll copy that into the notes. And you can see, so the key to the whole thing is you can clearly see that it's continuous and differentiable, no sharp breaks. But here's A and here's B, and they both happen to have the same value of Y, okay, which we're calling D. So in other words, f of A equals D, and so does f of B. Well, that means that no matter where you look in this curve, somewhere in there, you're going to find some point in between such that the tangent is horizontal, meaning that the derivative is zero. Okay. The slope of the tangent line is zero, meaning that it's horizontal. So it means as long as these conditions hold, we're guaranteed to find either a relative maximum or minimum inside this interval. That's really why this is important. Okay. So then they're going to show us another case where if the differentiability requirement is dropped from Raleigh's theorem, like here, if you notice, it assumed that the function is differentiable everywhere except potentially at the endpoints. Here, if you remember from the other day, when we have a sharp break like this, then the derivative is undefined at that point. Okay, hold on. Let me make that a little neater here. But in spite of that, um, there's a critical number in here. You can see, remember the way we define critical numbers. Um, if a number is a critical number, that means either the slope of the tangent line at that point is flat or horizontal, or else the derivative does not exist. So this C is a critical number, or sometimes it's called a critical value. And we could say the same thing up here. I guess we should come back here. Consistency's sake, we should label it. Um, and again, from the last section, I'll just remind you that a point C is a critical number or value. If one of two things is true, one of those is f prime of C is zero, or f prime of C is undefined. Okay, so either way, we still get a critical number. And that's how we identify, if you remember, our points that are either relative maxima or relative minima. Okay. So what Raleigh is basically saying is that under these circumstances, you're guaranteed that one exists in that interval. Okay. All right. So here's a numerical example we're going to look at. Here's the function. Now, this is a polynomial, which means that it's guaranteed to be continuous over any interval they give us. F of x equals x squared, minus 3x plus 2. And you know what we should probably do? Why don't we go take a look at Symbol Lab and see what this thing looks like? Just so we can visualize what they're trying to illustrate here. Y equals, or f of x equals, doesn't matter. Once again, it was x squared minus 3x plus 2. Okay, so you can see here that there's a relative minimum here, which is actually also a global or absolute minimum. But let's see what they want us to do. I think they're asking us to find this point. So, or actually, I think what they're really asking us to do is find these 2 points so that we can find an interval within which we can guarantee that there's going to be a relative minimum or maximum. So let's try that. Let's set this equal to 0. All right, so you can use the quadratic formula, or else you can just simply factor this. Um, no, wait a minute, that's not right. Oh, yes, 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 it's fine. Um, okay, now there's the reason why what you're trying to accomplish here is that when you multiply this out, of course, you want to reproduce this polynomial, but what we're really looking for is two numbers whose product is positive 2 and whose sum is negative 3. And that's exactly right. So now we know that x minus 2 equals 0 and x minus 1 equals 0, which means that the 2 points where this function will cross the horizontal axis are 1 and 2. And we know that these are the zeros or solutions of this polynomial. And in fact, we can go back and confirm that. You can see the points 2, 0, and 1, 0 are on this curve. So now, what would they like us to do? So Raleigh's theorem, okay, I see what they're doing now. Because the two endpoints are the same, at least they have the same values of y, that's what they were after. Okay. That means Raleigh's theorem applies to the function over this interval. And we're now guaranteed that there's a point in there somewhere where the tangent line um, is horizontal, which means that f prime of c is 0. So how do we find it? Well, what we're going to do is take the first derivative of this function. Now that we know how to do it, x squared minus 3x plus 2 is the function. Okay. Minus 3x plus 2. So we use the power rule and we set this equal to 0. Okay. And that means 2x equals 3, x equals 3 halves. So that means here, halfway between 1 and 2, although it doesn't have to be halfway in between, but here it is. The c, we don't know what the y is there, but the c is 3 halves. And what we can see from the graph is that at that point, the tangent line to that point is horizontal, meaning that this derivative or slope is equal to 0. And this is, of course, now a critical number. And you can see from the graph that this is a relative minimum. Okay. And there it is. Now, the mean value theorem, um, we've seen this before, but this time it has a kind of a different significance. This time we're saying that if f is continuous on the closed interval from a to b and differentiable in the open interval a to b, just like the Raleigh's theorem had the same assumptions, then there's a number in that interval c, but now instead of telling us, oh, by the way, I just forgot, there's one more difference here. In the mean value theorem, we don't require um, the two endpoints to be the same. Okay. So that is the big difference between the two theorems. As a matter of fact, you can see why we can't require that because if these were equal, then this would just reduce to 0. But that wouldn't do us any good, would it? Okay, so now this one takes a little thinking to understand what they're trying to tell us. So let's think about this for a minute. So let's just pick a function. And here's A and here's B, f of A, f of B. Now, somewhere along the way, we did discover that f of B minus A over B minus A is actually the slope of a secant line that connects or between A and B. All right, so we definitely did this, but you might have forgotten after all this time went by. That is the formula to calculate the slope of a secant line between those 2 points. So what they're basically saying here is this. Given this setup, we're guaranteed that there's a number in this interval C where the slope of the tangent line is the same as the secant line. Now, I didn't draw it as well as I could have. Let's see what they've got. But in English, that's what this means. Let me just see what they've got. Ah, here we go. So here they've got this function, whatever it is. Oh, 5 minus 4 over x. And the endpoints are 1 and 4. So the secant line between them has this slope. Um, I'll write this here to make it crystal clear that we're dealing with the secant. F of B, so think of this as A and B. Um, Therefore, F of B is 4. F of A is 1. Well, looks like they chose an especially simple case. It's 1. So what the theorem is saying is that someplace in here, we guarantee the existence of a point where the slope of the tangent line at that point matches the slope of the secant line. So you can prove it by saying, well, here's 5 minus 4x, or 5 minus 4x to the minus 1. And when x equals 2, we end up with 1, and which is exactly what we were aiming for. Okay. So what that also means in turn is, the two slopes will be the same. Okay. Now it doesn't mean the slopes will be 0. So we're not guaranteeing the existence of a minimum or a maximum. We're just saying that the tangent line and the secant line, for whatever endpoints we chose, the slope of the secant line, whatever it is, there's another point inside this interval such that the tangent line has that slope. That is the mean value theorem. All right. So yeah, so that's that. And now one of the consequences of the mean value theorem, although they're not showing us um, any applications of this, if you rewrote it algebraically, it would look like this. So sooner or later, we're going to run into a case where we need this equation, but not just yet. They just wanted you to see this. I guess it's like a coming attractions. All right, now, so they want us to try Raleigh's theorem here in this function. Okay, I guess it won't copy. Let's try this. Yeah, sometimes with these books, they'll introduce theorems like that, and then it might take a while before they show you an actual application of it. And the interval is -1, 3. We don't have to worry about continuity because this is a polynomial. What we do have to make sure is that f of -1 equals f of 3. And so let's try it. Okay, 0. And it equals 0. So that part is satisfied. So what we can do is find, I think they want us to find that point. So first we determine that Raleigh's theorem can be applied here. All the conditions are met. Well, then the next step is to find the point where this is the tangent line is flat or horizontal. So we're going to set the first derivative equal to 0. And that'll be our C. All right, so the correct answer is Raleigh's theorem is applied C equals 1. So that's A. Okay, great. Now here, they want to know if the mean value theorem can be applied to the function f of x equals x cubed. Now remember, this time we don't need to show that the endpoints are equal. So we just need to ensure that the function is continuous, which it is. Y equals x cubed looks like this. And the interval 0, 16 would be, let's say, so the secant line, all right, well, I didn't draw it that well, but all right. Um, Now, since A is 0 and B is 16, f of A would be 0 cubed, which is just 0. F of B is 16 cubed. Wow, that's a big number. 16 cubed, 4096. So we have 4096 over 16. Probably, yeah, that can be simplified. Let's see. 256, what do you know? So now we can find that point. We need a point where the slope equals 256. So we'll take the first derivative. I'll actually rewrite this as f of x. And based on the power rule, it's 3x squared, and then we'll set that equal to 256. Okay. Now, I don't think 256 is divisible by 3. No, wait, hold on. Nope. All right, we'll leave it like this. Now, normally when you take a square root like that, there's two roots, plus and minus, but we're only considering the interval from 0 to 16. So we only have to take into account the square root of 256 over 3. Okay. Oh, okay. So I guess they've reduced it a little bit. What do you know? 256 is 16 squared, so that helps. And that should do it. So that means it would be C. And there it is. Okay, we're good. Okay. Oh, by the way, I just noticed there's something else that we need to go over here. Normally, the convention is to avoid having radicals in the denominator. So we can fix this up by applying a process called rationalizing the denominator. I'm sure you've done this before. And basically, all it means is you're multiplying this ratio by a very carefully chosen version of one, the whatever is convenient. And you can see why we're doing it here because this leads us to 16 radical 3 over 3. So our answer wasn't wrong, but you see how they've got 16 radical 3 over 3. That's why. Okay, so that's that. So those two theorems are now in our back pocket. We know what they are, what they mean, when they work. Sooner or later, we'll run into a case where we can put them to good use. I mean, it's fun to know these things too, but so now we're ready for 3.3. All right. So now this is getting back to what we've been talking about. We're doing a lot of optimization in this chapter, finding minimum points, maximum points, etc. So they're going to extend what we've already seen in this section. So first we define the concept of an increasing or decreasing function. Okay. And of course, we have to get used to the way these results are listed. Then we can interpret it in terms of English. Increasing means formally, I mean, you can tell by looking at the graph if it never goes down, I guess. But this is the formal way of defining this. So what is this telling us? For any two numbers, x1, x2, implies, okay, so in other words, if you have something like this going on, whatever x I pick, let's say I pick this as my x1 and my x2, because x1 is a smaller number, that guarantees, and it doesn't matter which ones I pick, that guarantees that f of x2 is larger or f of x1 is smaller. Okay. So in other words, what it's saying is for any two x's, as long as x1 is smaller than x2, that guarantees that f of x1 is smaller than f of x2. No exceptions. Now, you can probably imagine then how you would define decreasing. If f of x1 less than x1 less than x2 implies the opposite. All right, so imagine you had something like this going on. So what this means is that no matter what x I pick, again, as long as x1 is smaller, it guarantees that f of x2 is also smaller. Okay, for every all the points in whatever interval we're considering. Okay. Now this doesn't have to apply to the whole function. It can be restricted to certain intervals of interest. Okay. But whatever interval we've chosen, as long as this behavior is true in the entire interval, then the function is said to be either increasing or decreasing in that interval. Um, Now, it's also possible for a function to be constant over an interval. Let's take a look at this. This is a very strange little function. So clearly, the way they've drawn it, it's decreasing up to the x equals a. Between a and b, it is constant, which simply means that no matter what x's I pick, f of x's are the same. And then after that, it's always increasing. So you can see that increasing or decreasing in these cases applies within certain intervals, not the entire function. And the other thing they want you to notice is that in the decreasing range, the slope is always negative. If I were to draw a series of tangent lines, they would all have negative slopes. Here, the tangent lines would be flat, and here they would be increasing. Okay, so that's the connection they want you to draw here. Okay, so now we can look at section 3.5, um, tests for increasing and decreasing functions. So what they're going to do here is show us another way we could identify areas in which a function is either increasing or decreasing or possibly remain the same. This time it's being expressed in terms of derivatives instead of a result like this. And so it makes things a lot simpler for us because with these two tests, we basically might have to go ahead and check every single pair of x's. Where here we can find out if an section is increasing or decreasing throughout the entire interval just by looking at the first derivative. Okay, so this is a very powerful test to see if our function is increasing or decreasing or remaining the same. So the way it works is that if the first derivative is positive for all x in AB, then f is said to be increasing on AB. If f of x prime, f prime of x is negative for all x in AB, then f is decreasing on AB. And then finally, of course, if f prime of x is equal to 0 for all x in AB, then f is constant on AB. So in other words, in the first case, we're saying that the slope of the tangent line is positive, then the function must be increasing. In the second case, if the slope of the tangent line is negative, the function must be decreasing. And if the function itself has a flat tangent line, then it must be constant over that interval. All right, so let's look at an example of this. We have x cubed minus 3 halves x squared. All right, let's write this down. Fx equals x cubed. Oops, that's minus. So they would like us to find the intervals over which the function is either increasing or decreasing. Now, before we go any further, why don't we take a look at the function on Symbolab? It's kind of hard to visualize what this thing looks like, but let's go look at Symbolab. All right, here we go. Y equals x cubed minus 3 halves x squared. All right, great. So we'll be able to see just by looking at it where it's increasing and decreasing before we do anything else. All right, so it's pretty clear there's a region in which it is increasing, decreasing, and increasing. So this is the point 0, 0. Actually, I'm going to copy this into my notes real fast. All right. So, in other words, what this test is telling us we need to do is check and see the slope of the tangent line. Here, for example, the tangent lines are all positively sloped. All right. Now, I'm not drawing it as well as I might. They're supposed to touch it. Let me fix that real fast. Try that one more time. These are supposed to be tangent lines, and you can see they all have a positive slope, and then all of a sudden, the slope is zero here, and then it becomes negative. And that continues until we reach this point where the tangent line becomes flat, and then all of a sudden, they're all positive. All right, so in this interval here, f prime of x is positive, x prime of x is negative. We should probably draw lines to separate them. And then down here, f of x, again, f prime of x is positive. So that implies that in the first interval, the function is increasing, decreasing, and again, increasing. So they want us to prove this, okay? So the first one we have to do is take the derivative of this function, okay? All right, so once again, it's x cubed minus 3 halves x squared. So applying the power rule, we'll see that the first derivative is 3x squared minus, now here, this one's a little trickier because it's 2 times 3 halves, x to the 2 minus 1. So we'll have 3x squared minus 2. I'm sorry, minus 3x. Okay, so this is the first derivative. So what we're going to do is find the 2 points here and here where the slope is of the tangent line is zero, meaning that the tangent line is horizontal. So we'll divide out the 3. We don't need that. Now we're going to factor this out as follows. Okay, so those are the 2 points where the slopes change. This is where x equals 0, and this is x equals 1. This is where the slopes change. Okay, if you notice to the left of x equals 0, the slope is always positive, then it's always negative down to x equals 1, and after that, it's always positive. So what we're going to do here, or at least one approach we can take, is we can test a number in each of those intervals to see what the slope of the tangent line looks like. Okay, so let's go do that. So they've set up this nice little table for us so you can see how that worked out. I guess we don't have to do it ourselves. We'll read the table. And so in the interval from negative infinity up to 0, meaning this part here, they have us randomly pick the element -1, because we know that that's in the interval, although it could have been any number in that interval. And we evaluate the first derivative at that point, and it proves to be positive. Okay, so our conclusion is that the function is increasing in that interval. Then we look at the second interval, which is 0 to 1. And then we randomly pick 1/2 because we know that that's in the interval, evaluate the first derivative at 1/2, and come up with -3/4, which means that, of course, the function is decreasing. And then when we reach 1, they will randomly pick the value 2, because we know that's clearly in the interval, and solve for the first derivative at x equals 2. And it proves to be positive. And so therefore, the function is increasing over that interval. Okay. So that's how we can tell the regions over which is increasing and decreasing. Okay. Because of our understanding of how the tangent lines work when it's increasing and decreasing, and the fact that it has a flat or is flat or has a slope of 0 when the sign changes. Okay. So that's really what this is all about. So for any question like this, you'll always end up doing the same thing. You'll want to break it up into regions. Even if you don't have a graph right in front of you, all you have to do is find where the first derivative is equal to 0. That will determine the regions that we need to test, and then you can just check the sign of the first derivative within each region, and you'll end up knowing whether it's increasing or decreasing in each of those intervals. Okay, so. And this, yes, they're showing it to you here. They've got the graph, and this is exactly what we were doing. From 0, -infinity up to 0, it's increasing. 0 to 1, it's decreasing, and then after that, it's increasing forever. All right, so this is just general rules that just follow along with what we just did. We find the critical numbers. We use those to determine the intervals, test the sign of the first derivative within each of those intervals, and that will tell us where the function is increasing or decreasing. Okay, now this is notation that you sometimes hear these terms. Monotonic. What is that all about? Well, sometimes you have a function that either always increases or always decreases. Okay, so here's a perfect example of that. Let me draw that on the slides, on the notes. So no matter where I test the first derivative, the slope will always be positive. Okay, so when that happens, there's a few different ways we can describe it, but one of the ways you hear it described is it is said to be monotonically increasing. And it means that, like we just said, there's no part of this function that's decreasing or remaining the same for that matter. You do run into this sometimes. Um, so, here they're describing it as strictly monotonic, increasing. If you instead had something like this, let's say instead the function is y equals -y². Well, of course, everything works in reverse. Here, the first derivative or the slope of the tangent line is negative for all x in the domain, which is the real number line. So no matter where I choose to put a tangent line, it'll have a negative slope. And so therefore we say that or you can describe it as monotonically decreasing. Okay. So those are two cases that we want to remember. Once in a while, you run into this. The function doesn't have any regions in which it is both decreasing or increasing. It's always doing one or the other. Okay, the first derivative test. Here we go. Now you have a function. Now, this is the same example we had a few minutes ago. It has a relative maximum at 0, 0 because we know that it's increasing up to point zero zero, and then it's decreasing after that. So it stands to reason that if the tangent line is positive everywhere to the left of a point and negatively sloped everywhere to the right, that must be a point where it reaches a maximum. That guarantees it that this is a relative maximum. And then down here for the relative minimum, everything works in reverse. So if the tangent line goes from positive to 0 at that one point and then to negative, then that point, um, let's see, what I probably should do here is um, change that to C to indicate that this is only true at a single point. And then if it's the other way around, so this is very awkward. I guess this is not the best notation. I'm just trying to indicate that on the left we have positive, then we go to 0, then we go to negative. Then the point is a relative max, otherwise it's a relative minimum. And then now what you're seeing here is referred to as the first derivative test. The first derivative test to identify maxima and minima. Okay. Now, like it says here, at this point, we call this a relative minimum because the slope is clearly negative to the left and positive to the right. So this is the more formal way of writing what I was just putting up there. Mine is a little bit less formal, but you can see that C is a critical number on a function that is continuous on an open interval. If it is differentiable everywhere except possibly at C, where there could be a sharp break, then f of C can be classified as follows. If the derivative changes from negative to positive, okay, at point C, that's the second case I have here. then this is a minimum. Otherwise, if it goes from positive to negative, that must make it a relative maximum. Now, sometimes you can have a case where it is positive on both sides or negative on both sides. It can happen. And if it does, then of course, this point C, f of C is neither a minimum nor a maximum. All right. I don't know if they have any examples right here. Um, but they want you to see several. Oh, here, this is good. They have everything we need right here. All right. So, you can see, all right, I'm glad that they did this because you can see that we went from negative to positive here, which makes it a relative minimum, positive to negative here, relative maximum. And here are two ways in which you see what's happened here. The tangent line is horizontal, and yet look what happened. The sign didn't change. It stayed positive. And over here, it stayed negative. So this doesn't count as either a minimum or a maximum. So it is possible to have a point like this, a critical number like this, which is not necessarily a maximum or a minimum. Okay. So now later on, we'll see how we classify these points, but for now, it's enough to note that that doesn't guarantee that this is a maximum or a minimum. It depends on the change in the sign of the first derivative. All right, so now they're going to throw, trigonometry. Okay, well, we'll see what we can do. Here's the graph. Here's the function. We're only going to consider it over the interval 0 to 2 pi. The derivative, the first one is a power rule. The second one is just the derivative of the sign. Okay, so first we need to find where the derivative equals 0. So let's do that first. All right, so they're telling us that in terms of radians, the 2 points we need are pi over 3 and 5 pi over 3. So I'll tell you what, I think we could stand to take a look at this function in Symbolab. It's going to be very difficult to visualize what it looks like. 1/2 x 1/2 x minus sine x. Oh my God. Now keep in mind, we're only supposed to be looking in this interval here, but still, that's pretty terrifying. I don't think I've ever seen anything like that in my life. Look at that. Now, 2 pi is approximately 6, so it's going to be from like here to here. I'm hoping that they have their own graph of this. Yeah, well, okay, I can see that over the interval that they've chosen from basically here to here. All right, I guess that looks right. Okay, my God, what a function, huh? So, the 2 points at which the tangent is horizontal are, as we saw, pi over 3 and 5 pi over 3. So we can see there's two, we need to define check this region, but you can see by looking at the graph that we're going from negative to positive and from positive to negative. So, I mean, we can tell just by looking at this graph. Um, I guess we can solve. Hold on a second. We need 1/2 of sine x, 1/2 of x, and the sine of pi over 3. Okay, well, that's our relative minimum, and the relative maximum is it's approximately 1 point. Hmm, I got something different. Let's see. Let me try that one more time. Oh, there it is. 3.48484. Okay, that's better. So this is our relative minimum, and this is our relative maximum. So what they would have done is just chosen some random term in these intervals and calculated the first derivative so you can see whether or not the tangent line has a positive or negative slope. Let's see what they actually did. Oh, well, they didn't even show it to us. But like if you could check yourself, if you just pick a random term inside one of those intervals, then you calculate the first derivative, you would see that the first derivative goes from negative to positive and positive to negative. So that's how we can identify them even without this graph. All right, I thought they should have at least shown us their calculations. I mean, really. All right. You know what? All right, let's do this one real fast. Man, so it's a well, the thing is it's a parabola that's facing down. That much is clear. But let's take a look at it in Symbolab. God, I hope I never see that function again. Negative 9x squared plus 54x plus 2. Oof. Well, I guess all we have to worry about is the region on either side of this point, 3 comma 83. So what we would have done is taken the first derivative, set it equal to 0, and we already know from Symbolab that that point is 383. We could have just plugged 3 into the original function, but we know. So now we're going to check the first derivative's sign to the left of 3 and to the right. So let's do 0 on the left-hand side. Okay, so just as we expected, the slope is positive to the left of 3. And then to the right, let's just choose, let's say 4. And we end up with a negative number. So that means we go from positive to negative. And that's how we know this is a relative maximum. Okay. All right. I guess that's all they wanted us to do. Oh, there it is. So yeah, D is the correct answer. Perfect. Okay. So that was the end of 3-3. And what else do we have here? Let's at least take a look and see what is coming up in 3-4. I think we'll have to save it for next time, but let's at least take a look at it. Oh, applications. Okay. Now, the concavity and the second derivative test. Now, what is this all about? Well, the thing is, the test we've been looking at so far, we know how to identify the points, the critical numbers, which can lead us to points that are either relative maxima or minima. This test that they're showing us makes it possible to determine at all these critical points um, which ones are maxima, which are minima, and which possibly are neither. So that's what this is for, to not just identify where the extrema are, but to tell which ones are which. Okay, so we need to know, like, is this a maximum or is it a minimum? but we're going to do it in a somewhat different way than what we're used to seeing. Instead of checking the sign of the first derivative, instead we're going to take the second derivative, and that will give us a number which will tell us right away whether we have a minimum, a maximum, or neither. Okay, so it's an alternative approach to what we're doing here. And you might prefer this approach to what we've been doing. So we're going to do this. I guess we'll save this for next time. Concavity and the second derivative test. All right. So I'll see you then.